Okay, Fred, so we have another opportunity to show that you can play our favorite game, Proton, Neutron, Electron, right? You can tell me how many protons, neutrons, electrons are in these different species, and then identify what this species here is going to be. All right? So, remember, very similar to how we did it before, but now we're dealing with ions. Unequal number of protons and electrons, right? So there's going to be charges on our species, and that's what makes them ions. All right, push pause, go ahead and fill out the missing blanks in this chart, and we'll see how you do. All right, are you ready, Fred?
Yeah, I'm ready.
Did you get a chance to look at it?
Yeah, I looked at it.
All right, what did you get for the number of protons for cobalt 60 with a +3 charge?
That's 27,
How did you get 27?
because that's the number on the periodic table.
That's right. There's 27 on the periodic table. That's the number of protons. Oh, and the number of neutrons is our 60 minus our 27, 33. How about the number of electrons?
Positive 3 charge means there's 3 more protons than electrons, so 24.
Very good, 24. How about this one? How many protons? Push pause if you didn't get that first one and you want to have a chance now because you understand a little bit better. Okay? How many protons in this bromide ion?
35.
Very good. And 81 minus the 35, that's our 46. That's how we get the number of neutrons. Again, this is our mass number. It's the sum of the protons and neutrons. With that negative charge, what does that tell us about electrons?
It means there's 1 more electron than there is protons.
Very good. 1 more electron than there is protons. So, 36 electrons. Very good. All right, so did you get the last one, Fred?
I think so. It's copper 65.
Copper 65, is that it?
Oh, you mean the charge?
Yeah, there's a charge on that, isn't there?
Yeah, it's going to have 2 more protons, so plus 2.
Very good. Copper 65 with a +2 charge because of the number of protons is higher than the number of electrons. Okay, good. On our periodic table, or some of the ions that form have multiple charge states. Now, we just looked at how we could predict what the charge would be for certain elements. But our predictions are really only good for these elements here. We can predict what kind of a charge they're going to have based on their proximity to the noble gases, right? We can do that for our nonmetals here, not just those ones, but all these nonmetals. If they form ions, we can tell based on the number of electrons they need to gain to attain a noble gas electron configuration, right? These metals here, all of these are going to form a +1, right? Because of their location. All of these metals are going to form a +2 because of their location, right? So that's great, but it turns out that we can't tell what the charge is on these elements in this area, or even these post-transition elements, simply by looking at their location on the periodic table. So we'll figure out how to identify what these charges are on these different elements at later on. But right now, what we need to know and see is that if an element is in this region, which we call the transition metals, or in this region, which is called the post-transition metals, all right, then we don't necessarily know what kind of a charge it's going to form when it forms compounds. Aluminum is different. Aluminum does form a +3 charge always. Its location is 13 protons here, and it can lose 3 electrons to have an electron configuration of neon. Okay, so we have chemical formulas that we've been using off and on different times, mostly just water, right? This chemical formula, though, tells us how many of the different elements there are in the a molecule or compound, right? Here's an example, CH4. This is a compound that's called methane. we can display it a variety of ways. We have a structural way here where you can actually see how the connections occur, ball and stick here, and a space filling model. This is really what the thing would look like if we could actually see it most, right? And this is the structure that most looks like it. Okay. Many elements consist in discrete atoms. However, some, which are called diatomic molecules or elements that form molecules, right, that are molecular in nature, go around in pairs. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, all of these are diatomic in nature. That means you don't ever find this, a hydrogen atom all by itself. If you find hydrogen in nature, it's always forming H2, a diatomic molecule of hydrogen. And that's true for all of these elements. There's also sulfur. Sulfur sometimes exists as not a diatomic, but an octatomic, a structure of 8 atoms elementally, meaning it's still just sulfur, it's all sulfur, but it comes in different sets. So, this is a hydrogen atom, this is 2 hydrogen atoms, H, 2H. H2, though, is 1 molecule of hydrogen. 2 H2s, 2 molecules of hydrogen. Okay? All right. We want to introduce you to this term empirical formula. Again, this is a chemical formula for water. Here's a chemical formula for a compound called benzene. Here's a chemical formula for a compound called acetic acid. It's the main acid that you find in vinegar. All right. But these are called the molecular formula of these compounds. It's what a molecule looks like. Benzene, let me show you what benzene looks like. Carbon, 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 all bound together in a ring. And then there's hydrogen bonds, or it's not hydrogen bonds, but hydrogens bound to each of these carbons like such. All right, this is the structural formula for benzene. All right, now the empirical formula is the simplest ratio of the different elements in the compound. So C6H6 has an empirical formula of CH. C2H4O2 has an empirical formula of CH2O. Okay. Isomers, there are different structural shapes that can have the same chemical formula but are different compounds. We call these isomers. So simply by being given a chemical formula, C2H4O2, we don't necessarily know what compound it is. All right. The periodic table. The periodic table is a collection of elements that allows us to kind of have a general feel for their properties simply by knowing what their location is on the table. And when it was found that elements existed and they began to try to isolate elements, when elements were isolated, they began to see patterns that certain elements had very similar properties to other elements. And when they began to organize these elements based on their properties, right? This is an example of one of the earliest periodic tables, right? Elements began to be organized according to properties. It was clear that there were blanks, spaces where, based on trends, elements existed, but they hadn't been discovered or identified yet. And because of this work that Dmitri Mendeleev did, Mendeleev is often referred to as the father of the periodic table, although there are others that would dispute that, and there were others definitely that were involved in the organization of trying to organize all of our elements together. Also, the periodic table is organized into periods and groups, which are our rows and our columns. All right. There are some important locations on the periodic table that we'll refer to and to help us communicate well. Our first two columns here and our last six in this region here are called our representative elements. They represent some chemical laws really well, so we use them and talk about them a lot. Transition elements. These are our transition elements. These are our inner transition elements. All right. Group 7 or 8 here. Over here is our noble gases. All right. We've talked about our noble gases before. Group 1 are our alkali metals. Alkali is the opposite of acidic. You guys have probably heard of the term acidic. Alkali is the opposite of acidic, and when you put these alkali metals in water, it creates acidity. So that's why we call them the alkali metals. Over here are our alkaline earth metals. These are our halogens. And there are different names for these columns as well, but these are the important ones that we'll want to remember. Our noble gases, which is the easy one. You've probably heard a lot about those. The halogens, the alkali metals, and the alkali earth metals. Those are the important families. Notice how these lanthanides and these actinides, right, they belong right here. And so if the periodic table were really to be laid out, it would look like this, but it doesn't fit good on our 8.5 by 11 piece of paper, and so we present it like this, something like this. Again, our nonmetals in blue, our metals in green, and our metalloids making up this staircase that separates our metals from our nonmetals. So here's a question, pretty easy. Just take a few seconds, look through there, the notes, and try to reaffirm the idea of where our alkaline earth metals are, where our halogens are, and so forth. Okay? Which of the following is correct? Okay, did you get to take a look at it, Fred?
Yeah, I took a look.
If you didn't pause the video at home, go ahead and pause it and take a look until you get an answer.
I think the answer is D. Fluoride, fluorine. Is it fluoride or fluorine?
Fluorine, right? Because this is not an ion. It goes to fluoride when we call it, ends in ide when we're identifying it as an ion. But this is not an ion. This is just the fluorine element. Yeah, so fluorine.
Fluorine is a halogen.
That's right. Fluorine is a halogen. Good. So D is our answer. Good job. That's a good place to stop.
Okay, see ya.